Okay. So Zoom can hear us. Oh, I guess Zoom can hear us. Yeah, I got a thumbs up.
Okay.
Fine. We just had that for the clicker. Wait, I'm using the Bonner clicker, and it was beeping low battery the whole time. Fortunately, Lena has, I don't know, spare batteries. Elena and Aaron have saved me a lot.
Slide.
You have to push that in.
Oh, okay. This is a battery pack?
Well, I guess it is, yeah. So we got to put it in a charger. That's okay.
Yeah. Sorry.
That's what.
This one? Testing 1, 2. Very successful.
I can also just give you this one for a second.
Yeah, but I'm also wondering.
Oh, question.
For questions. Testing 1, 2, 3. Does it sound like I'm coming through the mic at all? Yeah. Oh, okay. All right.
So for this TV here, can we turn it on so I don't have to show my back to everyone all the time? Just don't know how to turn that TV on. Whatever. Oh, okay. Yeah, all right. I haven't seen you in a while. Too hard to hug. Hey, good to see you. Any last minute recommendations? How was Hawaii?
How are you staying here?
Here for a month. A month? Tell you all about it, yeah. How was Hawaii? How was Hawaii? Those other faculty there.
Aren't you supposed to be up there?
I thought so. So should be 50 minutes. It could plus or minus 5 based on, yeah. hoping it goes shorter than longer. I'm hoping it goes shorter than longer, but when you do it live, it's always 18th.
Now it's going to try and change it. It's all going to fail.
Just for you. Whew.
Okay, well, good afternoon and welcome. It's my pleasure to introduce today's speaker, Chris Tunnell. Chris is one of our own. He joined the Rice faculty in 2018. Prior to that, he was a KICP fellow at the University of Chicago, and prior to that, a postdoc at the Netherlands Institute for Subatomic Physics. Chris received his Doctor of Philosophy in Particle Physics from the University of Oxford, and his work centers around the detection of dark matter. And his interests are not only in the physics related to dark matter, but in advancing the computational techniques that allow for experiments such as what he will be telling us about today. Most of his work has been with the xenon experiment. And it is his interest in computation and techniques that brought him to Rice as part of the data science initiative. During his time at Rice, he and his group have won a number of awards, noticeably an NSF Career Award won by Chris in 2021. So we look forward to hearing about dark matter and progress in paradigms of discovery.
Thanks for the nice intro. Make sure you don't trip on the way
I'll try.
down. So, welcome everyone. So today, is it too loud or is it fine? So today I want to tell you about dark matter and also paradigms of discovery historically and also what we're trying to do these days. So first off, the quick thing to know about dark matter is that this Hubble photo of stars and galaxies is not a picture of the entire universe here. It's all a rounding error on a greater picture that I want to tell you about today, and before the end of this talk, actually show you what we think, if you were to see everything out there, what it would look like. The other part of it is, I don't know how to get rid of that top thing, but anyway. The other thing of it is, how do you make discoveries? You make discoveries with people. Today I'm going to be showing you a lot of work from everyone in my group, because one of my main career objectives is essentially developing people to be able to pursue computational methods for making discoveries, which I think is actually sometimes harder than doing dark matter research itself. So we have senior researchers here, postdocs, grad students, and undergrads. We've had a bunch of people come through the group in the past few years, particularly undergrads around the pandemic time. And just since she's done so much for us, I had to make Elena an honorary member because nothing would function without her. So I want to start off with the first paradigm of discovery, empirical observations. And when I told my English postdoc that I was going to start with Galileo, he said, "Oh, you're going to go back to the Greeks," jokingly. Well, an old picture, this is developed around the 2nd century with Aristotle, was this idea of the Earth-centric cosmology, that the Earth was the center of everything. And it only took Galileo many centuries later to come up with a telescope to be able to peer out and observe the moons of Jupiter, orbiting Jupiter itself, to sort of break this vision that the Earth was the center of everything. By looking at things like the phases of Venus, we have the current model of the planetary system with the sun at the center. In this case, this is a case of discovering light matter, in a sense. If these planets, or if these moons did not reflect light, we wouldn't have been able to discover them at all. So that sort of limits the ways in which you can perform discoveries. However, let's dive into mathematical modeling for a moment in the discovery of what I call the first dark matter. So mathematical modeling, here I just mean you can write out your theories in some sort of way, Newtonian mechanics, F equals ma, Schrodinger's equation, or quantum electrodynamics. It's just a term and a sum, where this allows you to make predictions or check consistencies of the theory. So let's go back to the solar system for a moment. People were studying Newtonian mechanics, the forces on the planet Uranus. And what they noticed was that the orbit of it just didn't make sense based on all of the planets we knew. And when they added up all of these force diagrams from your intro physics courses, people were able to discover this very faint planet of Venus, which was its own type of dark matter of the time. This trend of you look for missing mass, and this is a type of dark matter, and it guides your probes on what you want to find, is a trend that we'll see throughout the talk. So, okay, getting to the third one, numerical methods. And this is where we're going to start really understanding the modern dark matter a bit. So what do I mean by numerical methods? So Pauli had this nice quote that I really liked, where he was saying that the underlying physical laws necessary for the mathematical theory of the whole of chemistry are thus completely known, referring to quantum mechanics. And the difficulty is only that the exact application of these laws leads to equations that are too complicated to solve. So in your intro quantum course, you've solved you've made solutions for the hydrogen equation, for the hydrogen atom, but when you quickly go to helium, helium-4 in this case, then you have to start adding in like numerical techniques to be able to make any predictions about this. A more modern example, let's talk about quantum chromodynamics. So QCD, lattice QCD in particular. So this is the theory of quarks and gluons. And only recently, in the last, I guess, decade or two, have we been able to predict the proton mass from first principles. And this is a very complicated numerical simulation, and it's a way of also making new types of discoveries. Additionally, this hasn't been constrained to just quantum physics, let's say. We've entered a realm where we can use numerical techniques to do, for instance, climate simulations. This is fluid flows and heat transfers, particularly into the ocean. And these simulations have gotten so sophisticated that we can really predict what the future will look like. In this case, with the climate crisis, a sort of worrying one. But the levels of details of these simulations, or numerical solutions, allow us to even say specific things about how Texas will be affected. So they've gotten quite advanced, and they've sort of gone into other fields as well. What I mainly want to talk to you about for the next few minutes is something called large-scale structure, which is one of the best bits of evidence that we have for dark matter, but we don't talk about it in these talks. At least I haven't seen a talk talking about it here. So what large-scale structure is, this is this picture here. This is an n-body simulation. So what an n-body simulation is if you have a particle in a box, and my hand is a particle, and another particle in a box, and then you just turn on F equals ma and let them attract to one another. You can start observing interesting features in the sort of emergent phenomenon. If you throw millions or billions of particles in a box, then you start getting to something like this. And what I mean here is, this is a picture of essentially the evolution of dark matter through time. So we start off initially with some quantum fluctuations in the early universe that create overdensities of dark matter, where these overdensities start gravitating towards one another and then collapsing on one another. And that's what you sort of see as time goes. And then you start developing these filaments here, which is the exact type of filaments that you're seeing in this simulation. So this is a picture of the universe if you could see everything. Think of it. I mean, each one of these dots is a galaxy cluster. So the sizes here are enormous. What's interesting is if we look at data, if you start doing survey astronomy, essentially survey the distribution of galaxies, you begin to see that the distribution of galaxies, statistical distribution, agrees with this type of model. And this is a pretty deep insight, because what this means is if we start looking at the history of the universe, in a sense. So time is going to the right. We have some quantum fluctuations that I mentioned briefly in the beginning, inflation, so then the universe starts cooling down. You have the Big Bang. At this point, just hydrogen and a little helium just get tossed throughout the entire universe. And if there was no dark matter, then that would be the end of the story, more or less. Stars would never start to form. They're not massive enough to really do anything, and we wouldn't be here today. Which is why you have, for about 400 million years, these dark ages, where very little is happening. After about 400 million years, dark matter has started to cluster enough that you form these giant gravitational wells that pull in gas that then starts interacting with one another and creating photons and things like this. This gets called the epoch of reionization. But it really kicks off the structure forming in the universe. It's dark matter doing this. Where then just throughout the billions of years that follow, these dark matter halos start accumulating more and more gas, and galaxies, as just where we know it, the material we have here forms. So galaxies wouldn't really form, at least in the way that we know them, without dark matter. Next, I want to talk about data-intensive science, specifically what we're doing within Xenon to challenge one of the leading theories of dark matter. So data-intensive science, what do I mean by this? So there's some examples that might come to mind here. For instance, we have colleagues here on the CMS experiment. This is a lead-lead collision, but just because it's messier, and I don't know, people like heavy ions. Where you have a detector with many, many channels that is just getting illuminated by these collisions, where it's just creating tons of particles, pions, and everything else that just permeate through the detector and create an enormous amount of data. And at least for proton collisions, I think the bunch crossings happen every 10 nanoseconds. So it means that every 10 nanoseconds, you're just having an enormous amount of data being generated by this giant apparatus. And we've heard of these before. This is maybe one of the classic examples you think of. There are other examples from astronomy, for instance, trying to compute, like looking at the full sky and trying to derive dark matter maps. There are many different techniques for doing this. One, just to follow up on the climate simulation for a moment, another interesting thing is that beyond, so particle physics or astronomy, these techniques have branched out into many other sciences. And I want to point out one interesting satellite, which is we essentially live stream the Earth continuously to observe methane release. You might say, why do we do this? Methane is an incredibly potent greenhouse gas, I think 20 to 40 times more potent than CO2. And in methane, it goes by another name of fossil gas or natural gas. And it's unclear, at least in the literature in the past few years, if natural gas is actually worse than coal. The way that they're trying to quantify this is by essentially monitoring the Earth at all times. And you can observe individual places that are pumping and see, like, there's a leak here, we need to fix it. Because a lot of the methane losses, it's not when you're burning it for fuel, it's on the transport along the way. So you have a very complicated problem that involves a significant amount of data and a lot of modeling that is a type of science that we're now able to do. Which means that then you can quantify things like the direct emissions of rice is around 70 future climate deaths per year. And these things don't actually include any losses from, for instance, factoring in methane or transport losses. Beyond this, which I think is an interesting result in its own sense, I want to tell you about what we do in data-intensive science on Xenon, which is much smaller than any of these other projects, but we're still able to do quite a bit. So this figure here is some data from the experiment. It's supposed to look fuzzy for the moment, so don't worry about that. Time on the x-axis, we're looking at about 30 microseconds of data over about 500 channels. So if you wanted to look at all of the data in Xenon N-Ton like this, so you would have to, let's say we made a video of it at around 30 hertz, roughly what a movie is. And then we put 100 people in a room, this is a really nasty experiment, and just let them watch this for 55 years, right? 55 years. If anyone's seen A Clockwork Orange, there are ways to do this. At the end of the 55 years, you talk to the room of 100 people, and then you say, has anyone seen a single dark matter interaction? That's a sense of the scale of the types of problems we're dealing with here. And the team, who's, at least in our group, who's contributed the most to the computing is all listed here. So this is a physics talk, not a sort of computing talk. So I'm not going to dive too much into the computing systems, but I just want to give you a sense for the types of scales of what we're doing here with relatively small teams. Additionally, there's an aspect of what this team is doing called team science that I just wanted to highlight explicitly here. So team science is something that's quite common in larger astro or particle collaborations and has a few defining features, but it means that you can solve a much wider range of problems. Often these teams are interdisciplinary. You want to be able to tackle some problem that isn't in the normal silos of funders or universities or anything else. You have collaborative integration. This is sort of like management structures within the experimental collaborations, which is why particle physicists, like, I don't know, which is why I guess the Allen Center wanted Paul, because he's familiar with also how to operate in larger organizations. You want to bring a diverse set of skill sets. You don't want to just be a bunch of physicists trying to solve a machine learning problem, because then you don't benefit from these other domains. You want to bring people in with a wide range of skill sets. a shared goal to unify you, like finding dark matter or the Higgs or whatever else, and dynamic configuration. And what I mean here is that science is constantly evolving, so you want to be able to change the teams or essentially how the thing operates to be able to pivot to whatever science you're wanting to do. And these are the defining features of team science, which we use extensively in everything I'm going to show you. But, okay, now you're wondering what physics can be done with this. So let's get back to dark matter. So I was just saying that essentially galaxies are dark matter plus some rounding error for us and stars and gas and planets and everything else. So if this is the Milky Way, a dark matter halo is sort of all around us. It's a spherical halo. And we sit essentially attached to the sun, as I was talking about before, in this disk. And the disk here is, I don't know, it's where all of the luminous matter essentially is. If you go out to West Texas, look out at the sky, the band you see is the disk, all the stars that we have in our Milky Way. An interesting point is the halo mass here is about 10 to the 12 solar masses, the mass of our sun. Whereas the disk plus bulge is about 6 times 10 to the 10, so that's 15 times less. Just for a sense of scale on essentially what is in our galaxy. But as I said, we're attached to the sun. The sun is moving through this disk. Dark matter also is virialized and moving around. Everything's going at around 200 kilometers a second. Dark matter is, which means this is speed on the x-axis and sort of a density on the y, which means that there's some distribution here of dark matter coming at us with the speed, which means that experimentalists should perk up their ears a bit and then say, oh, there's a flux of this stuff coming at us. What can we do? Can we measure it? So to measure it, you need to know what could dark matter be in the first place. So I'm going to take a minute just to sort of walk you through some ideas of dark matter and the different mass scales involved. I'm mixing up different types of units, but it'll make sense. I'll step through it a little slow. So this is dark matter mass on the x-axis. I'm going to start here at a solar mass, the mass of our sun, sort of on the far right. The Planck mass is sort of in the middle here. This is the mass of like a dust particle. This is the largest mass that a fundamental particle can have according to particle physics. You can't have a single particle more than this. 1 GeV is a proton or neutron mass. And 10 to the negative 22 is roughly, it's better to think about it in a de Broglie wavelength than an energy in this case. It's roughly the de Broglie length of like a dwarf galaxy. So it's the smallest objects that we know that have dark matter in them. I guess there's some smaller ones, but roughly. There's a wide range of theories that cover all of these orders of magnitude. Primordial black holes is one. This kicked off a lot because LIGO, these gravitational wave detectors, can actually probe these theories. So then if a theory can be tested, then everyone, at least in my view, starts writing theories that can be tested. You have black hole relics. This is black holes that decay down to around the Planck mass to solve some information theory problem. WIMPzillas, which the world-leading expert on WIMPzillas is actually in this room. Andrew, are you saying no? But I don't know. I think you wrote more than Rocky. WIMPs is what I'll be talking about more for the rest of this talk. So it's just well, at least when I started in this game, it was the leading theory of dark matter. Axions and ALPS. We had Frank Wilczek here, I guess last spring, who talked a lot about that. And B minus L dark matter at this very low energy, sort of vector dark matter, which sort of ties more into the types of things Mustafa is interested in. The reason why I'm showing you this is because essentially we have one experiment that we're talking about, windshine, which I'll tell you about later in the talk, that covers its very low and also very heavy regime. And we also have xenon, which probes this WIMP intermediate regime at around the electroweak scale that I'll tell you about now. So WIMPs are weakly interacting massive particles. The weakly is not necessarily the weak force anymore because our experiments have been so successful in showing it with, yeah?
What rules out going even further? Why not 10 to the minus 30 or solar mass?
So if you go, the trouble is if you assume it's one type of particle and you compute a de Broglie wavelength of it, you know that there are very small objects that have been observed, these dwarf galaxies, where they're seen that they have dark matter in them. So then essentially the de Broglie wavelength of whatever particle is dark matter can't be longer than that. And if you just do that simple argument, you get I don't know, 10 to the negative 25, 24, and then if you fund a lot of astro research, you start getting up to 10 to the negative 22, and then it gets a bit more complicated. But that's like roughly it. I think, I don't, well, I'm guessing here, but I'm guessing that it's just hard to accrete something that's so large, it would become unstable. But you'd have to ask one of the astro people then. So. Anyway, so on weakly interacting massive particles, the theory of these is you have these objects that are like 100 proton masses or so that are scattering with a nucleus in an experiment of yours. And theoretically, it's super easy. It's just elastic scattering of galactic-bound dark matter. The dark matter comes in, and like a billiard ball, it knocks the nucleus around. So on that sense, there's not so much to understand about what this type of model would look like on the theoretical side. The trouble is the experimental side, because you want to detect, this nucleus only goes like a few microns, and you want to observe this over a multi-meter volume. So you need to detect a faint, fast KeV, and if you're a particle physicist, KeV is not a unit you normally use, it's orders of magnitude lower, signal in a multi-ton scale background-free cryogenic experiment. Each one of these adjectives costs you millions of dollars and lots of people's time. And now I put multi in italics because since I first started using this slide, we now have a multi-ton detector, which I think is quite nice. Here's a picture on the right, but I'll talk about it sort of throughout the talk. So the people, I don't know, crazy enough to try to do this is us and the Xenon collaboration. We bought a drone and made a nice photo ourselves. It's not the easiest to spot, but I'll circle the Rice folks. So that's Louise, me talking to someone, Tina, Ivy, Peter, and Aaron. So this is, what we're doing is we're building an experiment in central Italy here. So this is a picture actually of me like having breakfast, reaching out the window and taking a photo. So our experiment is underneath this mountain here. And this is just to get you a sense of an idea of what the experiments look like before we dive into technical details. This is me with a Xenon 1-ton experiment, which is our predecessor that we've upgraded since, where it's about 1 meter by 1 meter, and just, I don't know, have a sort of picture in your head. But since Xenon 1-ton, which is something that we built and sort of run before I came here, but we analyzed it with the people who were here, sort of the data set, the full data set. Since that time, we've built the Xenon N-ton experiment. And I wanted to tell you a fun story. So a lot of you know Peter, and if you're not used to either from the pandemic or working in clean rooms, guessing who people are based on just their eyes, that's Peter. So at Rice, we actually had a Rice News article written because this was 2020, and Italy was the center of the pandemic. So it was a really dire time in many different senses. And at least the way that I recall it, I'm sure this is wrong, is that I messaged Rice News and said, you know what, this is an interesting story because there's like, I don't know, Peter's in Italy building Xenon N-ton. And what happened was that this article, this Rice News article we put out, actually got picked up by the New York Times. Will coronavirus freeze the search for dark matter? And I really liked this little excerpt from it, which is Dr. Aprile, who's a spokeswoman of the experiment, promoted Peter, scientist from Rice, to direct the team of people building the experiment. Peter reported back to his friends and family in Houston that his Italian colleagues were kindly translating news and new government regulations as they appeared, which was often. I think this was maybe June or so, I forget. It was really early on in the pandemic, so it was crazy. But now, thanks to Peter and many other people, we have the Xenon N-ton experiment. So I'm throwing around a lot of experiments. Let's just do a quick overview here. Xenon 10 was the first Xenon-type experiment. This is before I joined, but just demonstrated that you can measure these micron nuclear recoils. Xenon 100, when I joined, was the first experiment to show that this was the leading way to try to detect WIMP dark matter. It beat out something called CDMS. And essentially, since then, this technology that we and others have developed has been the leading technology of this sort. Xenon 1-ton was, well, also leading for many years the whole WIMP search, and Xenon N-ton is what we built now and what we've already have some results out that I'll show you soon, and what we're taking data for the next many years. And then this last thing on the right here, Darwin XLZD, is sort of our future, where if you want to ask a question at the end and you don't have any ideas, ask why it's 40 tons, because it's a really interesting insight into like American, European thinking. Anyway, one interesting point is that as these detectors get bigger, because you want to just have more targets for your dark matter, right, 62 kilos and just tons and tons, you need the target mass times your background level to be sort of order 1 or less, ideally, because you're trying to do a background-free experiment. So as these experiments are getting bigger, your background rates are just dropping by an order of magnitude every time, just for a sense of scale and like the types of issues we have to deal with. This will come back. So it's cutting off the title, but if it's unclear, I don't always see it, just raise your hand and all. So I want to tell you about sort of 3 types of results. There have been 4 papers that have come out of Xenon N-ton in 3 categories. The first one is our search for dark matter with nuclear recoils. So matter is nuclei plus electrons. So the first thing we look for is, do the nuclei sort of, I don't know, move. This got called at one in the news, Xenon's experimental triumph, no dark matter, but the best null result in history. I don't know if I fully buy it, but there's a lot of excitement on just having this be like a Michelson-Morley type experiment for the WIMP model. I'm going to walk you through this figure, which I think you people can see the bottom. So on the x-axis here is WIMP mass. On the y-axis is essentially coupling strength of the dark matter to matter. So you want it to go down. In these lines, and if you can't see the details of the lines, don't worry. There's a blue line for Xenon 1 ton, which was the leading experiment for a while. And then recently, within the last year or two, we've had the Xenon N-ton and LZ experiments both come online, which is exciting. The LZ experiment is essentially the American version of Xenon N-ton. And the way that these experiments work is very quickly you become sensitive to a lot of new physics with a very small exposure. And then you have to enter into some long run where you operate it for many years. So at this point, the shots are fired for the race starting or whatever, I forget the phrase, of Xenon N-ton and LZ both coming online. And then the real question is, who can operate these finicky detectors for the next 5 years? Additionally, you can not only scatter off nuclei, but you can scatter off of electrons. And I was already explaining why just various backgrounds in this detector are low to begin with. I actually think that a detector, it's the most radio pure. No one's achieved this type of background reduction before over such a large volume in this energy range. So I like to say sometimes that it's the most radio pure place in the galaxy. But I'm always worried that, I don't know, maybe there's someone else in the galaxy doing this. So the second category of papers is this searching an electronic recoil. This is recoiling electrons. And there's various reasons why this is interesting, but what I mainly want to point out is that right after coming out with this paper, we did a machine learning reanalysis, essentially, of the same data. So what we're trying to do is we threw the first result together. I mean, it's a correct result, but there were sort of many manual physical steps where different analysts, teams of tens of people would have to do different things to data selections and everything else. And we were able to replace a lot of them with, probabilistic machine learning. Essentially a discriminator between the 2 types of signals we see, which meant that we were able to greatly simplify the analysis and rerun it, get not only similar results, but efficiency bump of a few percent. This was discussed in a seminar yesterday, and Aaron is the person here today who you can ask about if there's more questions. And since we have these very low background levels in the experiment, it means that we can actually discover new types of phenomena. So one is specifically about double weak decays in Xenon 124. So there was a process called double electron capture that we actually discovered in our experiment. So the way this works is electrons are in this cloud around the nucleus, and there's some probability that the electron is in the nucleus. And if you square that, you get the probability that 2 electrons are in the nucleus, very small. That's double electron capture. It's a process no one had observed before. The half-life is longer than the age of the universe, and a few years back, I forget when, we got the cover of Nature for it. So just by having a really low background experiment, you can do quite cool things. So I want to tell you now about how the detector actually works. So that, Guido?
Yeah, maybe naive question. So why xenon? Like why xenon is giving you all the elements the best performance to that like VIPs?
So I'll give you the short version.
Chris, can you repeat the question?
Why do we use xenon? Which is a good question. But it can get, so one big reason is that since the velocity of dark matter in our galaxy is quite low, it means that the dark matter coherently scatters off of the nucleus. So you get an A squared scaling. So you want to use heavier elements. You want to use heavier elements. Then you say, why do you use noble elements? It's because they don't interact much. They're very easy to clean. You can do the cryogenics for it. The next thing lower on the periodic table, I think, is radon. So you don't want to do that because then your whole thing would evaporate. But there's a mix of experimental and other reasons. But I think the biggest thing to keep in your head is just the A squared scaling because it's coherent with the nucleus. So I want to tell you just quickly how a TPC works. And I want to use the analogy of a scuba diver to start. So you have a scuba diver underwater that you're watching from the surface. They are rummaging around. They have an oxygen tank and like a flashlight. And they turn on their flashlight. And at the same time, they're moving around, so bubbles are released. And you're on the surface and wanting to know, where is this person in the first place? Well, wherever the bubbles come up on the surface of the water is their XY position. And then if you're clever, have a stopwatch and time between when you saw the light from the flashlight and how long it took the bubbles to come up, then you also have their depth. So that's essentially how our detector works. So this is our detector, an illustration of our detector, where all of these balls on the top are photomultiplier tubes, light sensors. And yes, I added this animation right before. So in this case, a particle comes in, scatters off of a xenon nucleus, and the electrons are the bubbles, and the photons are the scintillation light, the flashlight. Let's see if I can do that again. Oh, maybe not. So this particle comes in, immediately creates a scintillation light, the flashlight that we can detect. And then after some amount of time, due to a strong electric field, where Rice was deeply involved in making these electrodes, we extract the electrons to the top where they're also measured. And then we get not only the depth, but also measurement of energy. So there's generally three types of experimental challenges. So there's three types of experimental challenges that I want to focus on today. One of which is localizing events. So this is the radius in the detector versus the depth. Within this blue box is our fiducial volume. This is where we consider it very clean because it's sort of shielded, self-shielding. The xenon on the outside of the detector shields the xenon on the inside. So very little can make it into the center here, which is why it's so quiet. But the outside of the detector, Teflon and copper and glass and other things, can be more radioactive. So you see that there's a lot of interactions happening on the outside of the detector, which is why it's so important that we have a TPC in the first place. And the person who was responsible actually for figuring out this position in XY is one of our students, Shuzhou. So we have localizing, which is a challenge, discriminating, which is another. So based on the amount of photon and electron, the size of the signals produced, you can tell the difference between electrons recoiling and nuclei recoiling. The electrons recoiling are this blue band, and then orange is where we would expect there to be a dark matter signal. Then the last real challenge we have, so it really matters what good measurements of these signals are important. The last bit is that this is a rate on the y-axis versus energy on the x going up to a few MeV. There's just a lot of radioactive decays that happen in any experiment, especially radio-pure ones, or including radio-pure ones. We do the dark matter search here on the far left, really below normal radioactive backgrounds because it's such a low energy experiment. And this means that if you mismeasure one of these big signals, you can accidentally make a small one. So signal processing and just understanding the data is quite important in the physics we want to do. And I want to walk you through how signals are made in this detector. So you start out with just particle physics, astrophysics. You have a dark matter mass, sigma, coupling strength, astrophysics, the local dark matter density, and some nuclear physics. And then if you want to simulate this detector, you would have to run it first through scattering theory. All you know is some dark matter parameters, and you want to know that there is some energy that's gone into a nucleus, for instance. But that energy in the nucleus, that's not actually what you measure, right? You measure that nucleus stopping in the material and creating Xmers and all this other thing, and then eventually scintillating and then releasing electrons. So there's a molecular atomic simulation that has to happen on the part of this NEST collaboration I'm part of that tells you just the number of photons and electrons you have. But you also just don't measure the number of photons and electrons. What you measure is something out of a digitizer. So then you have to essentially simulate the detector, optical, and electronics simulation to actually get this spatio-temporal data, that thing that I was going to flash before your eyes for the next 55 years from before. So this would be called a forward model, or just how, like, the processes that generate our data. But the measurement process means we have to actually go the other direction, which is the big challenge. So the detector data, this is petabytes, actually it's tens of petabytes, is the data I was showing you before, the time series data. And we need to somehow go back to number of photons and electrons measured, and then from there we have to go back to try to infer the energy, and then eventually we would go up to infer sort of dark matter properties. And depending on what type of scientist you are, you do different steps. Experimentalists always have to sort of model it all the way down here, just because we have detector data. When you're designing experiments, you can somehow skip this because you don't really know what you're going to do yet sometimes. And theorists, at least for a lot of papers, you can sort of skip all of this to begin with and just smear out your energies. So most of the projects that I'll be talking about for the next few minutes is just going to be like connecting different steps along this line, or these different blocks. Because all of the projects in our group is somehow, I don't know, going from different blocks. I wanted to originally tell you how a neural net worked, and I said, oh, how about I tell them in like one line how a neural net works using Einstein notation? And then this is an AI-generated image of what I thought your responses would be. This is sort of what my group looked like when I said I wanted to do that. So I just wanted to say a quick point on neural nets so people learn something about them. This is what we're in for some in a minute, which is that in principle, all you need to know for the rest of this talk is that neural nets are based on the idea of a neuron in a brain. You have different inputs coming in, and then you have this axon that sort of reaches out to other neurons to be able to connect to. And there's this idea of the artificial neural net, which is here. So you have the cell body, right? You have inputs coming in, X naughts, X1, X2. You have these weights, somehow to weight all of these different inputs that then come into this cell body where you sum them all up. Now, you have to apply a nonlinear function to this for the output, because otherwise it would just be a linear system of equations. And what I want to point out is, like, if you were to try to draw a line that separates the red dots from the blue dots, you just can't do that with like a linear regression or a sort of linear classifier. So it means that this idea of nonlinearity, in this case, these functions over here is like 0 below 0 or x above 0, mean that the representative power of neural nets is just greatly increased. So then the universal approximation theorem is just, if you take enough of these and strap them all together and make it big enough, you can represent any nonlinear mapping. Or you can view what I was showing on the left side as just nonlinear mappings between different types of data. So neural nets, in principle, should be able to represent anything. So now I want to talk about localizing events. So we have to localize every interaction in the detector. This is a picture. Every one of these is a photosensor of, without statistical fluctuations, sort of what, in this case, an electron, these are slightly easier to measure, look like in the detector. The trouble you get often is that these are all Poisson processes. So a lot of machine learning literature isn't actually designed for that, which is its own headache in itself. Because you're wanting to run this on millions of events, so you might just have one thing fluctuate wrongly because it's Poisson, small probability, maybe you get a 1. You need to be very robust because we're a rare event search. You never want to mistakenly find dark matter. So you can ask Zhao about this. What was interesting is that he actually came up with a new way to design neural nets where instead of tying if every one of these dots is a neuron, instead of tying them all to the one above them, or I guess below them, you sort of let them see some distance. This is called limiting the receptive field. And by doing this, you sort of use some physical intuition of light can only propagate so far, or the sensors can only see so far, before you get essentially train some neural net output that then you can use for all of our physics results. An interesting thing here is based on how far you let them see. So if it's 65 centimeters, the detector diameter, okay, then everything is connected to everything. As you shrink it down to maybe 20, you find out that your RMS, your uncertainty, is, well, about the same as if you'd done all of these different connections. So 0.25, that's about, well, the sensor spacing is about 8 centimeters, so that's a lot smaller than the sensor spacing for the sensitivity. But we're also more interested in robustness, but that's another. The interesting thing here is if you're doing embedded systems, you're building a little chip and you only have a little computational power, you can get the full power of a neural net for a physical situation with a much smaller network, much fewer parameters. Additionally, this is just predicting an XY in this case, but we're scientists. We want uncertainties on everything, which happens very rarely in sort of the deep parts of analyses and particle physics experiments. So I want to tell you real quick what time is it? I'm fine. What essentially a probabilistic graphical model is. It's a way of representing sort of the dependencies between statistical distributions. In this case, it's a simple example of like the grass is wet, depends on if it rains, or if the sprinkler's on depends on if it rained. So you can see, okay, the sprinkler is off if it rained. And the simple way to think about this is that if you somehow measure one, so you say that, okay, I know that the sprinklers were on, then you say, okay, well, then the grass, there's only two situations, then the grass is probably wet. You can view this as sort of a posterior in a way for a very discrete problem. So then you're starting to get, by just adding in a bit of information, you're starting to reduce you're able to narrow down on the types of possibilities you're getting. In these probability tables is something you can train with that simulation I was just telling you from before. So this becomes interesting because, not diving into the details, but you can build one of these graphical models or Bayesian networks for the specific position reconstruction problem, finding the localization problem. So this is what we sort of saw before, all of the different sensors. This is on Xenon 1 ton. An illumination pattern. And then Tina, with the help of Zoe, was able to essentially come up with, uncertainty contours for these events, which means that we can start fundamentally thinking differently about how we do our analysis with these fiducial volumes I mentioned before. We can start getting probabilistic methods deeper into the analysis to be able to extract more out of the data. Additionally, this is a project from Louise, who's co-supervised by Ezra Brianning from statistics. So one problem you have in detectors is how do you classify data? Like we have this really sophisticated model of everything happening in a detector, but if anyone here has ever turned on a detector, you find out that there's something you find that you didn't expect. Like reality is always very harsh to experimentalists. So what Louise did was essentially pumped all of the signals that we had into something called a self-organizing map, which found clusters in this data in a way that we were able to say, okay, the only thing to spot here is that these clusters, that the little spikes, every one of these little waveforms is just a signal. And neighbors are clustered next to one another. The key thing to notice is just that they're different in different colors. That's all you need to be able to see from there. And when you go through it, you find out, okay, some of these are photon signals, some of these are electron signals, and others are detector artifacts that sometimes we never saw because we sort of cleaned them out earlier. And we find out that in area versus rise time, this is just a parameter of the signals, blue is the photon signals and green is the electron signal. We find out that actually by using his technique, we beat the state-of-the-art type of methods that we've been doing forever. Which is pretty cool. And there's papers on all of this. Next, deepest learning. So Ivy has a qualifier on Thursday, so I got this a bit late, so I didn't stylize it. But I think the main thing I want to say is just that deep learning, at least in Xenon, like going down to really that spatiotemporal data, the waveforms, just because it's tens of petabytes or not many people, is very challenging. Just computationally understanding how to frame the problems. So what Ivy's been trying to do is take inputs, in this case, the spatial info, but it will eventually be spatial temporal, run it through a neural network, which is many layers of different operations that happen. Have one sort of smaller layer, I'll explain what that means in a second. This is called an autoencoder. So an encoder to some latent representation, then a decoder back to the original. And then you compare that the input equals the output, and then you can see if the input does equal the output, you can look at this latent representation, and it should be fully representative of your data in this case. So what this means is we're trying to find ways to compress our data, is one way to think about it. Can we have our data in a format that is small enough, that's fully expressive of all of the physics, that's also more manageable to be able to do everything? The next, I'm missing this. So on the last paradigm of discovery, I wanted to talk briefly about AI-enabled science, because I think everyone here is, well, at least I'm always shocked by how much AI and machine learning, how effective it is in a range of applications. It's more than just classifying stop signs now. I don't know if people here use ChatGPT. I use it quite a bit. It's just like mind-blowing the types of things that are possible, and it even shocks machine learning researchers in what's possible in these types of problems or also in the sciences. And there are really some like fantastic examples of AI being able to enable certain types of science. This is protein folding as part of the AlphaFold project, where when you start getting into n-body simulations, people have discovered techniques that really can accelerate these. And this starts helping you out with everything from protein folding to find new proteins to people are interested in material design, making search engines where you can type in, I want something slippery with this mass, and it suggests some materials for you, to drug design. You have two proteins with some receptor. You know what fits in here and here, but you need to sort of figure out what's in the middle. Like there's this whole class of materials and molecule research happening that is quite fascinating. Additionally, this is plasma research. With tokamaks, this is for plasma. You contain the plasma within the tokamak, and you have feedback of the magnetic fields such that it stays stably in the tokamak. People have been using something called reinforcement learning to do this. Essentially, let some computer learn how to stabilize the plasma. Additionally, this is a little hard to see, sorry. A big area has been solving differential equations, essentially like learning how to solve them without actually doing the numerical solving. This is a case of smoke transfer, essentially. So you have like fire, smoke is going up, and then eventually diffusing through the room. And if only because it's, well, not only because it's small, the difference between the top row and the bottom row, you can't really see. Top row is numerical solved, the bottom row is solved through the machine. So there's quite a bit happening in this realm here. But the thing that I want to talk about, at least for the last few minutes, since I'm almost done, is I've always been jealous of people who are on colliders, particle colliders, because things like jet classification or just track finding in general has been something that has been going on for, I mean, the first literature on this was in the 90s. So, your mic is still on? No. So the literature for this comes all the way back from the 90s. It's a quite mature area. But it's also sort of saturated, so you sort of say, like, what can I do here? In this case, this is using graph neural nets related to track finding. So I thought, you know what? I want to do track finding in quantum sensors. So I'm part of this collaboration called Windshine, which is mainly quantum scientists. I'm sort of the token dark matter guy. And coming from various DOE labs, some people here might Jake Taylor or Dan Carney, Raphael Posner, a bunch of people. So we're all trying to figure out how do we use quantum sensors. There's so much happening in the quantum world. Sensors are being developed that, with or without us, what can that tell us about dark matter? So let me start off with now what I call heavy dark matter. This is the Planckian, these WIMSILs. So in this case, we have a test mass that's attached to something or levitated. And what we want to do is, this white thing here is dark matter flying by. And you can do your force, like F equals, well, the two masses divided by r squared. You can essentially compute the force just from gravity alone that you would exert on this test mass. You find out, okay, the sensor mass, there's only so much to do. Maybe we can get up to a gram. But then this is why you're testing only heavy models, because they need to be heavy enough that they actually influence this test mass. And these techniques, at least optomechanics, has been used with LIGO to do fantastic gravitational wave experiments. So we're trying to figure out, like, what else can we do here? So the idea here is fine. The mass of the dark matter particle needs to be large. Then we end up with what is, I think, one of the best pictures in a physics paper, which is WIMSILLAs. This is one model of dark matter that Andrew is an expert on. So these models of dark matter, essentially nobody thought that they were testable. I think Andrew still thinks they're not testable. But anyway, we're trying to figure out how to test it. In particular, if you have a lot of these sensors, you run into this normal track finding. How do you find a track? Which sensor? You run by a lot of sensors. Can you actually see that going by? That's sort of the data science problem here. The way we've been trying to do this, at least we've been thinking more recently, we've run through a lot of technologies, has been magnetic levitation. Or we can talk about this, Joy Hong is the person if you want lots of experimental details. This is a setup. Magnetic levitation is something, as far as I can tell, is only done in the US, out of Vienna, Stockholm, and Leiden, and the Netherlands. But it looks very promising. So the general problem is you have some quantum noise. This is atto G, and I'll get into why that's only half crazy. It's crazy, but it's half crazy. Okay, this is 200, the scale is 200 here, and the signal you're looking for is going up to about 2. So you're looking for this very small signal in this sort of quantum noise. So it's finding tracks in quantum noise. Okay. But at least based on the analyses we've been able to do, and there's things up on this, it seems like we can propose, this is the same plot as before, dark matter mass versus coupling strength. Xenon 1 ton is up here in the top left. We find out that just for relatively modest setups, we can really start clearing out parameter space here by 2 by 2 by 2 arrays or 3 by 3 by 3 arrays. And the goal eventually, this is the Planck mass here, is to be able to get to the gravitationally coupled line of dark matter that our quantum sensors. But that's really on the heavy side. On the light side, which is another body of work, this ultralight, which is part of what you're asking, you can say, well, what happens if you have ultralight? Well, if you try to compute the number density here, so the number, we know the local density of dark matter. It's a fun question. Yeah. If you say, okay, I have this number density and within a de Broglie wavelength cube, sort of what's the occupancy number? You'll find out that if it's bosonic, there's just so much of it that it starts acting like a wave, which is interesting because as a particle physicist, I didn't expect to be doing, well, waves. But, so the whole idea here is that we want to test for vector dark matter, which is something we're actually in Mustafa, coincidentally, is one of the world experts on how to deal with vector dark matter, with what's called a B minus L coupling. So this is baryon number minus lepton number. And it's a complicated answer for why this, but essentially there are only so many types of if there is an interaction that can be detected, there are only very few of them that you could write down that don't break quantum field theory. That's the thing to keep in your head. The observable that you get from this is a differential acceleration. So what you'll have here is, this is differential acceleration between, let's say you have two of these magnetic levitated setups with one material here and a different material here. Then what will happen is you'll get a differential acceleration between the two because they're all located within this giant dark matter field. And then this is actually an observable, quantified by the differential acceleration, proportional to the coupling that we're looking. This is what we're looking for. Difference in D minus L depends on the dark matter mass. What's interesting here is that if we just look at frequency versus the noise PSD, the amount of noise we expect. When speaking with people who know how to build these things, try to model the noise, there's some amount of thermal noise or back action noise or imprecision noise. When we model all of these, what we find out is that actually, with something we could probably build in the next few years, we could set world-leading limits on D minus L. And for probably cheaper than the price of a Kalusian bridge. So what we have here is, again, mass versus some coupling strength. This is the world-leading limits, and we find out that we can actually punch into these, really with a modest setup. The parameters we're assuming here, resonance frequency around a hertz or so, bath temperature of a millikelvin, integration time of 2 weeks, and we're assuming we're trapping in a gram size. Which is partly why you need to do magnetic levitation. You do it optically, you melt it. I'm actually not next. Battery's fairly dead. This is a picture of us in Vienna, actually. Dorian, the postdoc, me, and the guy who built the setup. So it's actually a setup that's running. We're just hoping to tune it up a bit. So in essence, now that I have my mic, I feel like I need to say more. So I'm actually concluding here. So we've gone through various different ways of discovering. So this empirical observations and the fundamental limitations thereof, mathematical modeling and how we discovered Venus through this missing mass, understanding dark matter through n-body simulations, which with the cosmic microwave background is, in my view, the two strongest bits of evidence for it. Data-intensive science, how us within the Xenon program were really doing a great job exploring this model of WIMPs to the point that we've constrained it quite a bit, to trying to figure out like me wanting to do track finding quantum sensors and then finding out actually like you can build world-leading dark matter experiments with things people are building anyway. So since I promised people the photo, so at least according to me, this is a picture of the universe, if you were able to see everything. So I hope at least you've learned to appreciate dark matter in a whole new way, learning some new ways of understanding it, and thanks for your time.
So we have time for some questions. Randy?
So, can you describe the quantum enhanced detector?
Can I describe the quantum enhanced sensor? So I'll tell you, let me go to this one. So what it is, I'll tell you a little bit, but we can also just dive into a longer chat with Joy Hong at the end. So you have a magnetic trap, you have a particle here, and then you have a squid that picks up the movement of it. And the squid can be either a DC squid or sort of a microwave readout squid. And I don't know, it's cold. So I guess I can talk, actually, how would I show the assumptions in the...
How do you get the dark matter to be trapped?
So the dark matter is not trapped. The thing is, yeah, so I think the way to think about it is this is a particle physicist talking to you about quantum sensing. So but the people have been able to develop very sensitive accelerometers, right? So as long as you can measure the displacement, or actually worse than the velocity, but of just a trapped particle, if you can see it displaced a little bit, if you can see the acceleration of it, then this is what's predicted by well, actually both of these dark matter models. In the case of the heavy dark matter, you have an array of these, and then you're just looking for just the normal gravitational force laws of being pulled slightly as the thing goes by. So it's this wave going through, for the heavy one, it's a particle flying through at around 200 kilometers a second. That sort of sets the time scale and how long it's transiting. And then you're just looking for the displacement of the sensors along that. In the ultralight case, you have a coherent wave, so you're actually going to be seeing, if you have two different materials, because you need to have the trapped particles have to have a different charge under your theory, a different B minus L charge. That's the charge responsible for this theory. So as long as the materials are different, then the relative acceleration between the two will be slightly different, and then that's what's predicted. So as long as they can measure the acceleration as a function of time, we can look for correlations in these accelerations. In the case of the heavy case, it's along some track. In the case of ultralight, it's the whole thing moving sort of together, but different depending on the material.
Yeah, so I was wondering, this bound of 10 to the minus 47, somewhere there was a...
For the mass?
For this one tons or n tons of xenon that's setting a bound for the WIMPs. You don't need a chat, just so.
Yeah.
So I was wondering, like when
So
can
you're referring to this
correct,
figure
yeah.
here.
So I was wondering, when can you declare victory that WIMPs don't exist? So I was trying to put the radius of a nucleus and the number of nuclei in a ton of stuff and see whether how many decades you have to go to rule in or rule out. Is there some way to think about that qualitatively?
So there are There are a few. There are a few. Through the last decade or two, we've cleared out many orders of magnitude, and then you say, when do you stop, right? Just to repeat the question. So depends a little bit on how you want to think about it. At one point, you have to stop, because at one point, you're going to start seeing neutrinos from the sun or from the atmosphere. And then we'll do neutrino physics, but I love neutrino physics. I've done it. That's fine by me. But at some point, you'll be capped on how much this technology can do with sort of theory agnostic, if you were just to take it down as far as you can go. And that's what we're aiming for with the next experiment. That's essentially the last one that would be a credible dark matter detector. The question you have is, at what point do the theories stop making sense? Because originally, WIMPs were predicted to be here. And then essentially every time we do an experiment, that blob runs right below the line. So there's various, I think this is a feature of particle physicists in general. There's many different, complain a little bit about, not complain, but observe. In a lot of the phenomenological literature, people just tune knobs to be able to lower predictions. But I think we're already in a parameter space that you're getting into like fine-tuning problems. At least that's my opinion. That's not a wide opinion. But I think that at this point, for WIMPs, we're getting into the realm where if we start finding dark matter here, you start asking, well, why would it be there? Because it's not where you would first expect it. But that isn't necessarily bad, because, for instance, with solar neutrinos, when people were first trying to observe them, so people looked for the solar neutrinos at what you would expect by modeling the fusion processes in the sun. And then did experiments, this is Ray Davis, and found out you didn't actually find what you expected. Then he kept doing more and more experiments, and then found out that depending on the experiment, that it was either half or a third of what you would have expected. And then that ended up being Nobel Prize winning physics, the neutrino oscillations. So sometimes, like, we go in with a simple model of what dark matter might be. In this case, all of the dark matter is a WIMP. First off, our normal matter is quite diverse. Dark matter might be diverse too. I think the real way to think about this, I've argued over dinners so much about how far do we go and like what's the right way to think about it. I think the real way to appreciate this is we've built an incredibly sensitive detector to both nuclear and electron recoils. And what this means is that we're able to probe a wide range of theories. WIMPs is sort of our baseline. In neutrino physics, it was always looking for proton decay, and then suddenly you found a different type of physics. And along the way, we found nuclear physics. And I didn't go in planning on doing a nuclear physics paper, but we found something. And just by having very sensitive, low background detectors, just opens you up to a much wider range of possible things to find.
Very quickly, so we should probably talk about this offline, but I was struck by the 10 to minus 47 or 10 to minus 46, because I get 10 to the minus 26 from a radius of the nucleus, right?
This is centimeters squared.
Yeah. 10 to minus 13 centimeter is the nucleus of the.
This is also per nucleon?
I understand that, but what's left of 10 to minus 26 seems to be like 10 to the 20, which is approaching Avogadro's number very rapidly. So
I don't fully follow. But
so okay, well,
Willie,
we should talk about it.
yeah, I'd like to hear more.
So are there any other questions?
Particularly from students. If they're...
Students, is there something on chat?
That might be about the microphone.
Yeah, it might be about. But other questions for Chris? Going once?
No one, I even gave you a hint. Does anyone want to ask me the thing about 40 tons?
Maybe something still related to the quantum. So in which sense this is quantum enhanced? These detectors are quantum enhanced, because it seems that the physics behind the detection is still fairly classical. You have a macroscopic object that is levitating, and it gets a kick from a heavy dark matter particles,
exactly.
or you have like two different masses, and you kind of detect correlation. There are still classical correlation between them. because of the different masses if
Yeah,
it's,
it's
very
partly
light?
based on how I explained it, because there was just a range of topics. I think the real way to view this is to be sensitive. You need to be past the standard quantum limits. You have to start doing squeezed light and a lot of, like all of the noise reduction levels that are being pioneered at Oak Ridge and other labs. Like, we need orders of magnitude more noise reduction, which puts you into all of these fancy tricks that people like you do to be able to get that. So if you just said, like, if I just took the uncertainty principle, then said how well would it perform, it would be impossible.
So you plan,
So you have to be past the standard quantum limit.
so you plan to have like some type of quantum correlation thing, like that squeeze thing to go towards the isotope?
These are the types of things, like, we're floating different technologies, and it always ties down to who can build the best quantum accelerometer possible. But for instance, when we were doing optical cavities, this was a case where you really had to pay attention to, like, I don't know, what the literature on, for instance, trying to have non-disruptive measurements of the state, because the photons you put in will disrupt it, as you know. So, like, these types of problems are the real things that limit what we can do, and are not also not expert. It's more even. So the types of tricks you do is exactly the types of, I just want an accelerometer that I know where it is.
Okay, any last questions? All right, well, let's thank Chris again. And I believe there will be some refreshments outside, so please enjoy those.